In this video, I will do a quick review of kinetics and what they mean here in organic chemistry. And we'll go over the different orders of reaction. And lastly, we'll go over the different factors that can affect the kinetic of a reactions. So let's get started. What is kinetic? So kinetic refers to the rate. How fast does something happen of a reaction? So the rate of reaction. And it's important to point out that spontaneity has no control over the rate of the reaction. Thus, because something is spontaneous, it doesn't mean it'll be a fast reaction. It can be spontaneous but slow. For example, the process of diamond getting converted back into graphite. It is a spontaneous process, however, it's very slow and takes millions of years for that to happen. So your diamond is safe for now. Now, the reaction rate, it is not dependent on the spontaneity of the reaction. However, it is dependent on the concentration of the reactant. So in fact, changing the concentration of the reactant, that is the biggest factor that can affect and dictate the kinetic of a reaction. Because the higher the concentration of the reactant, then the more collisions that it would have at the molecular level. So basically more reactants will be able to collide with each other. And that is what needed in order for us to produce the products. And therefore, the faster the rate of the reaction would be. And for reaction, the rate law or the rate equation is determined experimentally by studying the effects of the reactants. And in fact, here is a generic reaction right here where A and B are combining to produce C and D. And the rate of this reaction mathematically can equal to the rate constant multiplied by the concentration of A followed by multiplied by the concentration of B. So again, C and D are not part of this because we can see that the rate of a reaction is purely dependent on the concentration of the reactant. And where X and Y here are the coefficient in front of A and B to make it the balanced reaction. So X is basically the order of reaction with respect to A, and Y is then the order of reaction with respect to B. And when we add X and Y together, this equal to the overall order of reaction. So that's what the rate of reaction would be. And the rate constant here is uniquely different for every types of reaction. So when we have a first order reaction means that the rate of the reaction is dependent on the concentration of only one substance. And in this case, the rate equal to Kr multiplied by either the concentration of A or B, but not both of them. So if it is the rate equal to Kr times the concentration of A, this means that only A have the effects on the reaction rate. Whereas when we double the concentration of A, the rate of the reaction will double. And changing the concentration of B has no effect on the rate of the reaction. So when that happens, this is then said to be a first order reaction. And the second order reaction is basically one in which that both A and B has the effect on the reaction rate. And doubling either A or B will double the reactions rate. So in this case, the rate equal to Kr multiplied by the concentration of A multiplied by the concentration of B. So both A and B contribute to the rate of the reaction. So that is then said to be a second order reaction. And again, so basically this is ratio to the first power and this is the first power. So when we add both this together, this equal to 2 and therefore it is the second order reaction. And in the third order reactions, for an example, the rate would then equal to Kr multiplied by A squared and B to the first power. So basically, if we were to have this rate of reaction right here, this means that when we double the concentration of A, the rate of the reaction would be quadruple. And when we increase the concentration of B, this would only double the rate of the reaction. So therefore, the order and the sum of this add together would then equal to 3, and therefore this is then said to be the third order of reaction. So these are the different types of reaction right here and how we classify them in the order dependent on the effects of the reactants on the rate of the reaction. Now, let's try some example right here. Dichloromethane react with diluted sodium cyanide according to this reaction below. And as we perform this reaction, we observe the following. When we change the concentration of the chloromethane, when it is double, the rate of the reaction is double. And when the sodium concentration of cyanide is triple, the rates of the reaction also triple as well. So here are a few questions that we need to be able to answer regarding this reaction. What is the kinetic order with respect to the concentration of chloromethane? So here in this case right here, we saw that when we change the concentration, when we double the concentration of dichloromethane, the rate is double. So we saw that clearly the concentration of dichloromethane has an effect on the rate of the reaction. And in this case, this is on the first order, right? So the first order is when you double something and the rate will be double. So that's what the order of reaction would be. So in this case, with respect to the chloromethane, this is first order. How about the kinetics with respect to this concentration of cyanide? Now in this case, when cyanide is triple, the rate is triple as well. So that's very similar to double and double again. So in this case, this is also first order with regard to the concentration of the cyanide. And then overall, the kinetic order of this reaction will then be second, because it is first order with respect to chloromethane and first order with regard to cyanide. So adding them together, this would be overall a second order of reaction. And lastly, how will we write the rate equation for this reaction? Then the rate for this would then equal to Kr, and whatever Kr would be. And in this case, the concentration of both the chloromethane and the concentration of the cyanide, because both of this has an effect on the rate of the reaction. So that's how we would be writing the rate equation for this reaction. And now, let's go over the different factors that can affect the rate constant. The rate constant has an effect on the overall reaction rate. So therefore, let's analyze the different effects or the different factors that can affect the rate constant and the rate of the reaction. So first one is activation energy. Activation energy refers to the minimum amount of energy that is needed in order for the reaction to proceed. So this, it can be seen as the barrier or the hump between reactant and product. So given two examples that have different activation energy. On the left, so again, the activation energy refers to the energy different from the reactant into this highest point right here. And that is the transition state. So the amount of energy difference from the reactant into the transition state. This is then known as the activation energy. And in this case right here, there is a small difference in energy between the reactant and the transition state. So this is then said to have a smaller activation energy. And for reaction that have a smaller activation energy, it would then have a faster reactions rate. Whereas, comparing this to another example, so here in this case right here, we have a different potential energy diagram, where now we can see there will be a larger activation energy in here. And this would then correspond to a slower reactions rate. So that's the activation energy and how it can affect the rate of a reaction. The smaller the activation energy, the faster the reactions rate. And now, temperature. Temperature can also have an effect on the reaction rate as well, in which that the higher the temperature, then the faster the rate of the reaction. And this basically, the reason why this had an effect is simply because at high temperature, there will be more molecules with sufficient kinetic energy to react. Because basically, we would then see that at high molecule at the molecular level, they're colliding into each other as the reaction is proceeding. And therefore, at higher temperature, each molecule would then have higher speed or velocity, and therefore they can collide better or collide faster, and therefore correspond to a faster reaction rate. And so here is a plot right here that shows the concentrations of the entire sample and what happened to them between lower temperature and higher temperature. So this is the distribution curve right here. So we can see that, and when high temperature, let's say here is the minimum amount of energy needed to react, and that is what the activation energy would be. So at high temperature, if we were to be looking under the area under this line right here in red, then we would then see there be more percentage of the molecule that now have enough activation energy in order to proceed. Versus lower temperature, then now we can see we have smaller concentration of the molecule that have enough energy. So this is how a temperature can have an effect on the rate of the reaction. And one rule of thumb is that by increasing the temperature by about 10 degrees Celsius, you will be doubling the reactions rate. And the next one is the steric consideration. Steric here refers to the steric hindrance that has to do with the geometry and the number of alkyl substituents that occur on the reactants, and also the orientation of the reactant as well. So basically, as the reactant are coming together, how easy for them to come together, it's dependent on the steric and the geometry of how that can happen. So the steric can also affect the rate of the reaction because it affects collision frequency. And the more steric something would be, then we would imagine it'd be more difficult for them to collide, and therefore the slower the reaction rate would be. And lastly, catalyst. Adding a catalyst can affect the rate of the reaction as well. And so catalyst can speed up the rate of the reaction without being consumed by the reaction. And that's important for us to notice that a catalyst is not consumed in the course of the reaction. And how the catalyst works, it basically by providing an alternate pathway that has a smaller activation energy. And this is why that it actually can have an effect on the rate of the reaction. For an example, so let's say here is the line in blue represents the reaction and energy diagram of a reaction without a catalyst. If we were to add in a catalyst, now the reactant will go to a different path that have smaller activation energy right here, but it still leads to the same formation of the product. So note that the energy difference between the reactant and the product are basically the same thing, whether with or without a catalyst. But with a catalyst, it simply goes to a different path that have small activation energy, so therefore it can happen faster. Okay, so, and again, remember that the energy of the reactant and product remain the same. Therefore, the delta H of the reaction would also be unchanged, but it now can happen faster. So these are the 4 different factors right here that can affect the rate constant of the reaction, and also that affect the rate of the reaction overall.